Good evening, ladies and gentlemen. Welcome to the evening session, which again I hope is a fun session, not too heavy after a long day's work and a nice meal. It's a discussion, demonstration of the what has become known as the Cranfield Rock gramophone, phonograph, developed initially at Cranfield but sponsored by Townshend International through Max Townshend here. What I want to do this evening is to describe briefly the history of how this came about and lead you through the engineering which has ultimately come to the fifth model, the Mark V, known as the Avalon, but more about that later. And I want to talk about some of the engineering, the principles which go into this. I'd also like to say something about the whole subject of sound reproduction, hi-fi, high fidelity as it's often called, and I want to point out one or two myths about this and one or two of the misconceptions which are very common at present, especially in the UK. So this all began in 1977, some 11 years ago, when I gave some of my students the rather arrogant brief to design the world's best record player. This was a record player for black analog discs, black vinyl discs, not the compact silver discs, which at that time had not been invented. So a number of students worked on this, and they came up with a prototype, which certainly didn't sound particularly good, but it certainly had something. And this was then heard by Max Townshend, who from that point in time acted as sponsor. A further student, in fact two further students worked on it, and from this came the first one. This was by now Mark III, which was put onto the market. This sold tolerably well, but as we'll see on the slides, it was, if anything, over-engineered, and to get the cost right, it had to be re-engineered to provide more value for money. We'll see what was done for that, and then finally we'll move next door to the other lecture room, and we'll be able to see. There will not be an audio demonstration, I'm afraid, but we will see the Mark V, the Mark IV, and the Mark III rock gramophones, and we'll be able to talk about them and have a look at them. So let's talk first of all about sound reproduction itself. And the sound reproducing system, as shown here, what we're trying to do is to put together the elements, as we can see on this picture here. We have a signal source, which could be microphone, perhaps a radio tuner, the gramophone pickup, which we're talking about this evening, tape replay, and of course nowadays we might add compact disc to this as well, and there could be one or two others. The signal from whichever of these has been selected is fed through into a preamplifier, which will have a number of controls. And one doesn't necessarily have to have all of these controls. I guess there'll be a volume control, certainly. Not all of the others are necessary. The output from the preamplifier is then fed to the power amplifier, which beefs up what is still a very small signal into a larger signal sufficient to drive the loudspeakers, shown here as left hand and right hand for stereo, and of course we have power supplies. Now what are we looking for? Well, the basic parameters I think are shown here. We want an adequate output power. Now audio power is something which is very much misunderstood. When you think that the Royal Festival Hall in London, filled with some 5,000 people, can be completely filled with everyone listening to just 1 watt of audio power, just 1 watt. When you think that a grand piano played at maximum volume is only giving us something like 50 milliwatts of audio acoustic power, then you wonder why people look for amplifiers of 100, 200, in the case of pop groups, 1,000 watts output per channel. And the answer, of course, is in the efficiency of the loudspeakers. In the main, loudspeakers are extremely inefficient. You're lucky if you get a loudspeaker which is more than 1% efficient, and many loudspeakers are less than 0.1% efficient. And so the majority of the power that you generate in the amplifiers is going to end up as heat and not as acoustic power. So certainly, anyway, we want sufficient output power for the situation in which we're playing. Now, a full symphony orchestra can, in fact, generate peaks, instantaneous peaks of many tens of acoustic watts. And if we were to reproduce these, even in a large room, and this room is not too small, then it would simply bring the ceiling down. A man in America tried this recently, and he did indeed bring his ceiling down, laths and plaster, everything, because he tried to provide the full dynamic range of the orchestra. It can't be done. And so in practice, we have to compress. In other words, we have to slightly increase the volume of the very quiet sounds, and we reduce the volume of the loud sounds compared to real life. But certainly, anyway, we need adequate output power for the situation. We want inaudible distortion. You'll notice I haven't put a figure there. People talk about 0.1% distortion, 0.01% distortion, and so on. It depends very critically on the type of distortion which is there. If you think about harmonic distortion, for example, Beethoven often wrote music. He would play a tune, and then he'd double the tune, the same melody in octaves. So now if you think about the notes are being played and the octave of the note, double the frequency is being played as well. That, to a first order, is 100% second harmonic distortion, isn't it? But it sounded good. And Beethoven knew it sounded good, and the other composers also knew that. And so we can say that 100% second harmonic distortion actually is a good sounding thing. But if you then introduce distortions, especially odd harmonics in the teens, 17th, 19th, 21st harmonic distortion, this is very, very audible in very small quantities to a human ear, and it sounds bad. And so when we talk about distortion, to say maximum harmonic distortion less than 0.1%, 0.01%, I would suggest it is meaningless. Think of Beethoven. An adequate linear frequency response. There's another slide showing this, but briefly here, the human ear is responsive to sounds from a frequency of something like 15 or 20 hertz at the very low end, up to, well, it depends how old you are. Children can hear up to 30, maybe just over 30 kilohertz, but as one gets older and gets more and more white hairs like this, the man-made fibers, which I have on my head, they are man-made, I made them myself, then we find that the hearing falls away, and I can just about now hear 8 kilohertz. However, having said that, if you were to play me, and I suggest to most of you, a note of, say, 27 kilohertz, you wouldn't hear it. And if I played you 28 kilohertz, you wouldn't hear it either. But if I played you the 27 and 28 kilohertz together, you would hear, you'll be sensitive to the 1 kilohertz difference tone. Now, just as an aside, at the very end of the talk, I'll say something about compact discs. But compact discs cannot, by their very nature, by the standard, they cannot reproduce anything above about 20 kilohertz. Now, when you think that orchestras are giving out notes up to well into the 30 kilohertz range, nothing above 20 kilohertz can get onto a compact disc. And so the 27 and the 28, which together give the 1 kilohertz difference tone, simply are not present. I'll say something more about compact discs a little later, but just bear that in mind. We need a good transient response and a good stability. And transients are sounds like that, a sudden sound, a sudden rise. And it's important that the sound reproducing system is responsive to that sort of sound, and of course it must not go unstable. There should be inaudible hum and noise. Now again, I haven't quoted a figure because I've simply said they should not be audible. As long as they're not audible, then you aren't worried about them. There'll be resonances in the system. Nothing is perfectly dead. Even corpses resonate, I'm told. And so you want to make sure that if these resonances are there, and they will be, they must be adequately damped so that they don't obtrude into the listening scene. There should obviously be facilities for the proposed input signals. We saw some of these on the previous picture. And then perhaps suitable controls, maybe filters, and so on. But you'll find that most of the upmarket equipment does not have tone controls, and they only have very rudimentary filters. It's probably desirable not to have many frequencies coming through below, say, 10 or 12 hertz, and it's probably a good thing to have nothing above, say, 30 or 40 kilohertz, otherwise radios can come in. But apart from that, you should not need filters or tone controls in addition to this. If the records have been correctly made with the right balance of tone, then they should not be necessary. And people say, but what about the room? Surely the room itself needs correcting for. Well, yes, but the fact is, if the Allegri String Quartet, instead of playing at Milton Keynes tonight, they were playing here, we wouldn't worry about tone controls and filters, would we? We'd say they sound bloody marvellous, and we'd listen and we'd clap and a lot of applause at the end, and we're not worried. But as soon as you put loudspeakers here, playing a record of the Allegri String Quartet, then everyone gets concerned about filters and controls and treble and bass and so on. But if the record's been properly made, then this should not be necessary. Now, I talked about the frequency range, and on this picture here are just indication. I'm sorry, it's a fairly busy slide, and it may not be very obvious from the back. Here we have instruments, the piccolo, flute, oboe, clarinet, moving through the woodwind into the brass, the French horn, trumpet, bass trombone, bass tuba, then onto the percussion, the xylophone, timpani, and then through the harp into the strings, the violin, viola, cello, and the double bass. Along the abscissa, we have frequencies. It's about 30 hertz on the left-hand side here, and 33 kilohertz here. The dark shaded parts of the spectrum show the fundamental frequencies playable on those instruments, but can you see at the high frequency end there are the harmonics above there, and it's these harmonics which distinguish one instrument from another, and it's essential that our system should be able to reproduce those harmonics accurately and of course without distortion. And how do we do this? Well, I'm talking about black disc reproduction tonight, in which we have a stylus, and here is one of the many international standard stylus dimensions shown here, in fact, within an international standard groove. And the idea is that this stylus has got to track that groove. And what do the grooves look like? Well, here's a picture of the surface of a typical black or brown gramophone record. And just look at the detail in those grooves. And what we have to ensure is that our poor little stylus, here we are in the previous picture, has got to track that information, bearing in mind that on the black disc, on a good black disc, you will get frequencies up to about 30 or so kilohertz. And I can assure you that with modern pickups, variations of the groove of the order of tens of nanometers are audible to the human ear. So it is indeed a precision engineering requirement, and we've been talking this week in our mechatronics course about precision engineering. And when I mention the word mechatronics, if you think about it, it's the bringing together, the integration of fine mechanics with electronics and control. That is surely what is being done by the gramophone record player, and indeed what is being done by the entire audio sound reproducing chain. I mention the chain, and one other little point I'll make here, and that is that people say, come and listen to my amplifier, or come and listen to my new pickup, or even come and listen to my record. Generally, you can tell if people are interested in music or hi-fi, because the man who's interested in music buys a loudspeaker to listen to his new record, whereas the man who's interested in hi-fi buys a record to listen to his new loudspeaker. There's a slight difference. But having said that, the fact is you can't listen to an amplifier, or a loudspeaker, or a record, or a pickup. All you can listen to is a complete chain, which has a record at one end, a pickup, an arm, a turntable, amplifiers, and loudspeakers. In other words, what I showed at the beginning of this talk. It's only on a complete chain that you can actually listen. You can't listen to any of the items in between. So it is rather a fallacy to say, listen to this amplifier, or even to take an amplifier in a system and unplug it and plug another one in and say, oh, I can tell there's a difference. That difference may not be in the amplifier itself. It may be in the interfaces, in the interconnections, the influence of the cables, for example, on that amplifier, which is making a difference in sound rather than the item itself. It's a very complicated situation we have here, and it can't be easily and glibly dismissed like so many people try to do. Now, let's talk about, first of all, turntable design. The principal factors we have to consider are the drive system. How do we connect the motor to the turntable on which the record is going to be placed? The drive motor should be AC or DC. The bearing itself should be a plain bearing, a rolling element bearing, a fluid bearing, perhaps a magnetic bearing. The acoustic mounting system, what I mean by that is that we have our record player in the room, we have loudspeakers perhaps in the corners of the room or somewhere, and there's sound in the air. There's also people speaking and walking around and other sounds, no doubt. And these sounds in the air, including especially those from a loudspeaker, are going to influence to some extent the record and the pickup on the turntable. And if we aren't careful, we do get a howl-round effect. We have feedback right through that loop. We have to make sure that we have isolation to all of these extraneous sounds, including the record itself. Otherwise, we can be in trouble. And of course damping. I've mentioned resonances. We have to make sure that the inevitable resonances are going to be damped. And so we minimize these resonances. We want to minimize wow and flutter, which are speed variations. Wow is the term given to long-term speed variations, flutter to higher frequency speed variations, and these can be very audible. And of course we want to minimize rumble. That is bearing rumble on the main bearing itself. Otherwise this comes through as a growling, grunging sound underneath the music, which is not very desirable. First of all, let's talk about bearings. Now this part of the story goes back in fact to 1972. I was working in CUPE then, and I designed a fluid bearing looking approximately like this. In fact, there's a number of versions. Let's describe this one since the slide is there. On the bearing, we require a thrust and a journal component, and the thrust component was given by these spiral grooves there. Now, these grooves there are in fact etched. They're etched into the steel of the thrust plate of the bearing, etched to something like a half a micron deep using ferric chloride on an appropriate spiral form. And when you insert this male component here into a plain closed cylinder with a viscous oil, we use silicone oil, but it could be other oils in between, and with a radial clearance of the order of 2 or 3 microns, it's not critical, then we find that when we start rotating this, and this of course there's a flat plate across here, when we start rotating it in the appropriate direction, make sure it's the right direction like clockwise for the gramophone record, we find that the oil in the grooves is forced to the center, and this provides a thrust, an up-thrust, and at about 7 RPM it lifts off, and so by 33 1/3 RPM, just to think of a number out of space, it is going very nicely without any metal-to-metal contact between the rotating part and the stationary stator part of the bearing. And furthermore, these two sets of herringbones there and there with a good L to D ratio between them, again, as it starts to rotate, the oil is forced by the grooves into the center, and we have 2 annuli of high-pressure oil at those 2 points, and these provide the journal part of the bearing. And so when it is operating, you can put an avometer to measure resistance, to measure ohms between the stationary and the rotating parts, and you will get effectively infinite resistance. There is no contact at all. So this means that as far as the rumble is concerned, there is no metal-to-metal contact, and so we can forget about rumble to all intents and purposes in our reproduction. This in fact was developed from an idea by Moiderman at Philips. He initially produced this in 1968, I think, for very high speed, like 300,000 RPM air bearings. And I took the idea and developed it further down to use at the much more prosaic slow speeds of 33 1/3 and 45 RPM for black gramophone records. Here is, in fact, the first bearing which we developed, and here you can see the thrust plate on the bottom of the simple cylinder here with the 2 herringbones there. I said they were etched. These are the masks used in a very simple printed circuit arrangement, same as you make printed circuits. We expose photoresist on the cylinder through these 2 masks, and then immerse the cylinder into the appropriate solution of ferric chloride for the right length of time, and this generates the spiral and the helical grooves as I've indicated. So this was the original setup for the bearing which the students produced. There is the turntable called the platter, in fact. This is the spigot on which the record will sit, and here is the bearing itself, the original cylinder with its clearance shown there, the spirals being on the side, the spiral on the bottom, and the herringbones on the side. And just as we're looking at this picture, let me also draw your attention to a point which I'll raise a little later on, and that is that in order to control the speed, we decided to do this digitally, and we put a reflecting grating on the underside of the platter, which I think you can make out there and there. And yes, there were 2 diametrically opposed reading heads, one there and one there, for reasons which we've come to know and love during this week, I hope. And so we were able to get a sequence of pulses as it rotated and have a digital servo. In fact, it was a third order digital servo was used to control the speed of this system here. And the motor used was in fact the one which we passed around the room this afternoon in our lecture. It was the so-called brushless DC motor, which you all know is a brushless AC motor. In fact, that was the motor used initially, directly driven onto the turntable spindle running in its hydrostatic bearing. In fact, sorry, hydrodynamic bearing. In fact, this was wrong. And I'll come back to this a little later on. But this was a development situation, and we had students doing this work, carrying out the measurements with the aim of getting a component, a product, onto the international market and selling it at a profit. We moved on from there, and for various reasons which are discussed in the paper which I have handed out to you, but I won't go into too much detail here. This bearing was in fact sold, this concept was sold to a British company, the Garrard company, which then in fact sold out to Gradiente in Brazil. And for various reasons, which we never understood, they decided not to go ahead with the commercialization of this particular bearing, which is a pity, because had they done so, we would have picked up some rather useful financial royalties. So we never in fact made it for there. But when we wished to, this is jumping ahead a few years, when we wished to market our own turntable using this bearing, they were not disposed to let us have a license even on our own invention. So we had to look to another invention instead, another design. It's rather galling when you invent something really good and then you find you can't use it. If you put all your best effort into that particular invention, you then have to invent something different. And the problem is to make it as good. Well, what we invented, in fact, was a PTFE Teflon disc, which I'll pass around the room. And if you look at this, you'll see there's a series of pads are molded onto this, a series of stepped ramp pads, which I can draw on the board here to give you an idea. Obviously not to scale. There's a center line, and we had the situation where on the bottom of this there was a series of effectively serrations like that, and as it rotated against a plane face like this with an appropriate oil lubricant in between, we were able to build up pressure within these steps here, within these wedges, and this provided liftoff. I'll pass this around the room, and I think you'll see when you look at it and indeed feel it with your fingernail, you'll feel how it actually worked. So this slide here then shows this alternative type of bearing we were forced to go to. The journal part of the bearing fits down into here. We're looking on the top of it. This is a female part, and the part which I'm passing around the room, the Teflon disc, in fact ran against this beautifully ground annular surface around there. Here now is the male part being inserted into there, and the Teflon will be up at about this level like that, and that will run against this annulus there with oil of the appropriate viscosity already inserted. Here again is, I think it's Max's grubby fingernails inserting it, and now you can see the complete turntable with the spigot for holding the record, locating the record, and here is the male part of the bearing being inserted down into the female stator. Now let's move away from bearings and talk about drive systems. There are two, well, strictly three alternative ways of doing this. One of them I've already mentioned, and that is the direct drive, where you have in our case, a brushless DC, or if you prefer AC motor mounted directly onto the spindle. But in most cases, you don't have that. You'll either have a belt driven from a motor in a position such as that, or alternatively, you will have an idler, a solid, maybe rubber, idler wheel, which provides a drive between the motor spindle here and the inside, in this case, of the turntable or platter. This, I think, we can dismiss fairly quickly, because inevitably the motor has got its own bearings. These will not be particularly good bearings, and the motor will be running quite fast for a number of reasons. And so if we aren't careful, the vibration of these bearings is going to be transmitted through the idler onto the turntable platter itself, and hence onto the disc, and provide a vibration we don't want, and hence an acoustic noise we don't want, onto the signal in the pickup. So dismissing that one, we look at this one instead. And this now is a good idea, because with the belt, a compliant belt made of rubber, neoprene, something like this, could even be an O-ring, for example. What we have here now is that the vibrations of the motor bearings can in fact be damped, can be filtered out by the action of the belt here. So this in fact turns out to be a very good way of doing it. And the majority, if not all, of the high performance turntables currently on the hi-fi market, or even the hi-fi upmarket, are in fact of this type of drive. So in fact we went to this, and here is the belt being placed onto, one of the two pulleys on the top of the motor. The motor extends down below the slide here. Two pulleys, because by having a different diameter top and bottom, this gives us a chance of rotation. And you'll notice the belt itself operates directly onto the periphery of the turntable, onto the platter. Why do we do this? Think of the Abbey rule, which Professor McEwen talked about. Now, he talked about this in terms of measurement, but in fact there's a similar, which Abbey never postulated this, but there's a similar situation regarding forces. You want to make sure that all forces act if you can, in the same plane. Because if all forces act in the same plane and through the same point, then you can get no turning moments or couples, can you? And so it's always a good thing, if you can possibly arrange this, to have no turning moments or couples. If, for example, as often happens, this belt operated on a subplatter below the main turntable, let's just go back. If it happened operating on a subplatter such as there, then if we're playing records on the top here, which we are, then we have this offset between the drive and the plane of the record itself. Ideally, we want to drive directly in the plane of the record. Now, in fact, we can't quite get directly in the plane of the record for obvious pragmatic reasons. We can, however, drive directly onto the periphery of the turntable. And so on the first, I think the first marketed model, this is what was done, and it's shown here. So here's a further picture, and in fact the pulleys which we saw a moment ago are in fact located underneath this cover, and we'll see this in the demonstration which follows this lecture presentation. This motor, of course, you saw before, and was passed around the room this afternoon, in fact. This is the direct drive motor which we originally tried out, and I have at home a prototype system. I think it's the second prototype, which does indeed use a motor such as this, driving directly onto the spindle of the platter. And this, in fact, although it gives a very, very good performance, in practice we found that even though we were driving it with as pure a sine and cosine signal as we could, remember that the drive signal is given, the overall torque is given by the sum of the squares of the drive signals, and we agreed that sine squared plus cosine squared equals 1, and therefore in theory there was no torque ripple. In practice, for a number of reasons, including, for example, a finite number of poles and coils on the motor itself, there was just a very, very slight ripple, and without the belt, without the flexible belt, which we saw on one of the earlier pictures, to filter out this ripple, it was just audible on very, very careful listening tests. It still sounded pretty good, mind you, but it was just there. And so on comparative tests, we decided, for that reason and for the fact that this was quite an expensive component, that we ought to in fact go towards the belt on future models. I mentioned that it was driven on a digital servo, and in a very schematic way, and I don't want to dwell too much on this, there is a paper written on this, which I guess I could find if I were asked nicely. This illustrates what we had. This should strictly be vertical here, I guess. That is a turntable showing the grating encoder disc, as it were, mounted on it. Two diametrically opposed reading heads, if you recall, and these were connected in quite a complicated system, which ultimately gave us a third-order digital servo. And this provided, as I say, a very, very good response, but which, however, was not quite good enough. The idea of having a grating on the underside of the turntable is a good one, to generate a frequency proportional to the RPM, the rotational speed of the turntable. I do recommend that. But if that were in fact used together with a belt drive from an outboard motor onto the turntable, that probably would give one of the best possible design solutions to this particular problem. I'm not sure if anyone has done that, but it's certainly something worth thinking about. Now the chassis itself, the plinth, if you like, on which the turntable and its motor and ultimately the arm, we haven't come to the arm yet, but we'll come to that, on which they're mounted. We decided, of course, being at Cranfield, that we ought to use granitan for this, so-called synthetic granite, which, if you recall, was developed initially by the Studer company at Thun in Switzerland. Cranfield did some work with that company to help develop it and carry out some tests, and I think I'm right in saying that Cranfield was the first licensee, certainly for the UK, for this particular material. We decided to use this on the initial prototype rock gramophone, both for the platter itself, the 12-inch diameter rotating platter on which the records would be placed, and also for, as I say, the plinth on which it is all mounted. This is a picture of the mould which was used for the plinth, made of aluminium principally, with inserts, as you can see here. The whole was coated with an appropriate release agent so we could use it more than once, and after moulding we achieved a result looking something like this. The two cutouts here and here were for arms. This was a prototype situation. We decided to have the possibility of applying two arms, hence two pickups, so we could do comparative tests between arms, or indeed between pickups, on the same turntable. Very, very useful that. You play a record, you have it being played twice. I've even seen three being played, 120 degrees spacing between each pickup, and this does give a chance to do pretty accurate comparative tests at the same point in time. The human ear has a very poor, or the ear brain perhaps has a very poor memory, and even over a few minutes one can forget what music, speech actually sounds like. But having a direct comparison where you switch from one to the other, this is the only true accurate way of doing it. This was the cutout for the motor drive itself, the bearing, and these I think were for the reading heads for the grating on the underside of the turntable. It was also mounted on 3-point support, but we'll come to them a little later on. Oh, this is the underview of the same component. Now, that was the original, one of the original prototypes. This was now coated, surrounded with a wood surround, which you can see here. This, in fact, is the next version, was again made of granitan, was surrounded with a wood surround, and as I've described earlier, the bearing was the Teflon disc which I've passed around the room, and this is the housing for that bearing. And here you can see the two pulleys, which you've already viewed on one of the slides, on top of the motor, which extends down below the top plate so you can't actually see it there. That is the on-off switch, and this hole is for mounting the pickup arm. And the name, you can see, the Rock, has already been added to it. Now the underside of this, this is the under chassis on which was mounted within the component we saw on the previous slide. And I showed this because here we can now see the motor, an AC motor, AC synchronous motor. There are the two pulleys on top, and the belt is going to come from either of these pulleys onto the periphery of the turntable, which will in fact be above a center line, something around that position there. And this picture especially shows the positions there, there, and there for the 3-point support, equispaced around the centroid of the complete system for very good reasons. If you, obviously 3-point support, I hope Pat McEwen has convinced you that this is a good idea, even though his car has 4 wheels and not 3. as I said this morning. It's important, however, to also to have the 3 points of support equally spaced around the centroid. Otherwise, if you think about the situation where it is being subjected from the mounting base, the mounting bench or table, to a vertical vibration, which often happens. For example, you have your record player in a room where a dance is taking place. That's normally where I think where most record players seem to end up, providing music for a dance, or what passes for dancing these days. Then if you have the center of gravity offset from the center of these 3 feet, then you find that subjecting it to a vertical motion will in fact generate a tilting and twisting motion, which is not a good idea for the stability of the pickup. So it's easy enough. These things are so easy. It's very elementary schoolboy physics, schoolgirl physics, really, but and mathematics. But and it's easy enough to do at the design stage. Simply to position the feet, doesn't matter where they are, simply position them so that they are equally spaced about the centroid of the center of mass of the total system, and then you're in business. This is a view from the very underside. Here again we can see the mounting points for these 3 feet, and now looking through we can see the underside of the granitan, the synthetic granite, completely out of view normally, so it didn't have to be finished. You can see the particles here. You recall that it's made of 95% is graded granite chips, ranging from several millimeters across down to sub-micron size, and graded so that they fit together in the right way on the Roman bridge principle, where you have large particles and then interstices filled with smaller particles, those interstices filled with smaller ones still, and so on. 95% is that, and 5% is a special epoxy filler which holds all of those particles and glues them, as it were, together. You can also make out the wooden surround here as well. Another view here, this shows the motor, and again the pulleys on top. I don't think we need to dwell on that. And I said that the turntable, the platter itself, was made of granitan. This piece of rock cake was in fact a slice, as it were, cut from the 12-inch diameter platter, as it were, as a piece of cake. I'll pass this around the room. I think you may have seen this material before, Paul, somehow. Yes. So let's move on to the arm itself. I'll come back at the end of discussing the individual components to talking about the complete player. So now let's talk about the arm. What do we have to worry about here? We have to worry about the inertia of the arm. This is generally expressed as the equivalent mass at the stylus, but it amounts to the inertia. You might say, does it matter? After all, if we think of the arm, let's just draw a picture of a tone arm, so-called, which will typically look something like this. There'll be the so-called arm tube. There'll be some mounting at this point here for the pickup cartridge. I'll show it like that, and so we know what we're talking about. There is a rather large stylus, like there at the end of a cantilever. There'll be some sort of pivot arrangement, perhaps here, so let's draw a center line at that point. And then there'll be a counterweight at the end. This is very, very simple. Let's draw the bearing something like this. And the idea is that the counterweight is such that we get the appropriate force there, traditionally measured in grams. I know grams are not force, but it's traditionally measured in grams, and a pickup will typically play at a so-called stylus force pressure. I know it's not force or pressure, but that's what they say, of between, say, 1.5 and maybe 5 or 6 grams nowadays. And you say, well, provided we adjust the counterweight here so that we get the appropriate downforce there, does it matter? Well, of course it does matter, because now, say, perfectly balanced, we were to put a 10 kilogram mass on there, and we were to put an appropriate, be larger of course, something like maybe 100 kilogram on there, and get it perfectly balanced, so we still have the appropriate, say, 3 grams there. You might say, because you've still got the appropriate force there, it doesn't matter. But of course it does matter, because no records yet made are perfectly flat of uniform thickness or indeed are concentric. It just doesn't happen. And so in practice, and you all know this as you've watched the record being played, not only does the stylus gradually move from the periphery towards the center, preferably stopping before the label, but in fact you, not they don't all do, but you also see it's gently moving up and down, don't you, and in and out by just a few degrees each revolution. Now, if that poor little plastic disc here, that little diamond stylus, has got to move the inertia, which I've shown there, then clearly this is just not on. So you do have to think about the inertia. I make this point because so many people do, in fact, end up with arms with very, very high inertia, and they claim that because they happen to have a 3-gram tracking force here, that it doesn't matter. And I am demonstrating that it does. In fact, let me rub them off so that we know it's not a good thing to do. So we want to talk about the inertia. Friction, obviously, the bearing, well, I've switched the light out, but you can remember the bearing there. We have two bearings, in fact. One is the horizontal bearing, which actually allows vertical motion, and the other is a vertical bearing, which allows the horizontal motion, in other words, allowing the arm to move from the outside groups of the disc towards the innermost ones. The friction of those bearings is clearly very important because the only force available to overcome those is generated by side pressure between the stylus and the groove walls on the disc, and we don't want to have higher forces there than we can possibly avoid. The stiffness is important, in other words, its resistance to intrinsic resonances. We don't want this arm tube, for example, to sound off like a tuning fork, because if it does, if there's any chance of it being put into resonance, excited, as we say, by, for example, a note at that particular frequency from the record being played, then it will, and this will distort. We'll come back to this point, but this will distort the sound. We need the arm, the pickup, the coupling between the pickup and the arm itself. In other words, this connection here, we've got to consider that. And in fact, side thrust compensation. Hang on to that term. I'll come back to this a little later on. Now, if we look at the replay geometry of a black disc, it's a sobering thought that the original cutter, cutting a disc, you start off with a smooth, uncut disc, 12 inches diameter, and you actually you turn this into record. And of course, you don't make the records directly. You go through a mastering and pressing reproduction process, replication, I should say, process. The original cutter, in fact, traverses a linear radial path, as shown there, just like cutting a scroll or doing a facing cut on a lathe. But in practice, of course, when you come to replay this with an arm which is pivoted at the point here, then of course it's going to trace out a radius as is shown there. And so straight away we have a distortion, an error, a built-in systematic error between the original path of the cutter and the radial path of the stylus from the outer to the innermost groove. So let's think about that. And let me just point to two particular aspects here. There's an overhang, in fact, between, when you take this right to the center, it doesn't go actually to the center itself. There is an overhang there. It misses the center by a particular amount, which we'll talk about. And there's